Good morning. Today's lecture is based on linear block codes, very important concept in the communication systems. So let me just uh, do the slideshow actually. Okay. So let's talk about linear block codes. Now what happens, this is the block diagram of a communication system, digital communication system, in which you will do the digital format. We have done in this course, we have covered the digital formats. Source encoding you covered in the last semester. This is the block which we will be discussing now, which is channel coding. Linear block codes fall into that category of channel coding, and correspondingly, you once you do the source encoding at the transmitter side, you will have to do the source decoding at the receiver side. In the similar fashion, you will do the channel coding from the transmitter side, and you will do the channel decoding at the receiver side. And then you will pulse modulate. We have all studied the concepts involved in this bandpass modulation involving amplitude shift keying, phase shift keying, and frequency shift keying, QAM, and other modulation schemes with memory. And at the receiver, you will need to demodulate and detect, and then uh, this is the transmitter side, and the other side is the lower side is the receiver side. And channel coding is basically done to mitigate the effects of noise that come from the channel. So whatever the noise will be introduced into the channel, whatever the bits will be corrupted, right, into while the signal travels through the travels from transmitter to receiver and through the channel. So channel coding is done to remove the errors, to detect the errors and correct the errors. Right, so that's why the name is channel coding, because this is related to the errors uh, in errors due to the channel. Right. So let us go deep into the concept. So this is channel coding, transforming signals to improve communication performance by increasing the robustness against channel impairments, noise, interference, and fading. So I have already talked about this. We will not do the waveform coding, which is basically transforming waveforms to better waveforms, right? Rather, we will come straightway to the linear block codes, right? Just to briefly discuss that why channel coding is important. So if this blue curve is there, so this graph is between the signal to noise ratio and the probability of error. So this orange curve actually gives us when you do not do the channel coding. When channel coding is basically, you must be aware of the fact that we introduce parity bits into the into digital data. So parity bits are used to detect and correct the errors. So basically, channel coding is based on that concept, and we will discuss in detail the various types of codes and how to decode the information. So this curve basically shows the orange curve is for uncoded data, and this blue curve is for the coded data when you do the channel coding. So you clearly see that for when you do the channel coding, the signal to noise ratio requirements decrease drastically. So the performance of the system overall actually improves. And we define it in terms of coding gain. Coding for a given bit probability of error, the reduction in the signal to noise ratio that can be realized through the use of the code. So what is the gain? So this is EB by N0. So that means that this point will be given by this orange curve when you uncode, when the data is uncoded, and this part is given by when the data is coded. So the difference between the two, the signal to noise ratio requirement, is actually termed as the coding gain that you achieve when you code the input data to mitigate the effects of noise. All right. Now, there are some basic concepts to be understood while we go for discussing about the linear block codes in detail. Okay. So what are the concepts in the digital data? The digital alphabet is containing two elements only. One is 0 and 1. So digital data can be expressed into 0 and 1 only, and that is termed as the alphabet. So there are two elements in the the digital alphabet, and that is also called the binary field. So the set 0, 1 and what are the operations involved in the while we discuss the coding? It is addition and multiplication. So 0, this addition is basically the XOR or the modulo operation. 0 plus 0, 0 XOR with 0 is 0, 0 XOR with 1 is 1, 1 XOR with 0 is 1, 1 XOR with 1 is 0. And multiplication, 0.0 is 0, 0.1 is 0, 1.0 is 0, 1.1 is 1. So binary field, this field, why this is called binary field? Because there are two elements in this set. Binary field is also called the Galois field, and this is how we can represent it. Galois field, the argument is to telling us that there are two elements in the set. Now, let F be, so what are fields? Let F be a set of objects on which two operations plus and this dot operation are defined. So F is said to be a field if and only if F forms a commutative group. So that means A plus B is equal to B plus A, right? Forms a commutative group under operation. So commutative group under the addition operation and the multiplication operation. And it has to be distributive also. That means A dot B plus C, A dot B plus A dot C. So you all know about the commutative property and the distributive property. So the elements, it will be called as a field when the elements follow this property of commutativity and the distributivity. All right, the elements have to be distributed. The operations are distributive. All right. Now the question is that what is vector space? I will just discuss about the vector space in terms of, let me just skip some of these slides here, and I will come back to these slides to explain what is vector space, what is vector subspace, and the spanning set and basis. Let me take this example to explain. So what is a vector space? Vector space means, for example, you have four bits in a set. So let's say you consider a case where there are 4 bits. How many combinations will be there? There will be 16 combinations. 0, 0, 0, 0, 1, 0, 0. So all these are possible 16 combinations, right? And this V subscript 4 is the vector space. That means how many total number of combinations of bits are there? That is called as the vector space. So how many elements are there in this vector space? 16 elements are there in this vector space. And why this is called 4 tuples? 4 tuples means 4 bits are there. We are in general, we are at present talking about a binary field in which 2 elements are there, but we can talk about other fields also. For example, if we consider all the elements of the English alphabet, that means 26 elements will be there. So in that case, that will be a field of 26 elements, Galois field of 26 elements. But since we are considering only binary data, that means the field contains 2 elements only. And when the field 0 and 1. So if we consider a 4 tuple vector space, that means 4 bits are there. I am now particularly, I will concentrate only on the binary field. I will not talk about other fields. All right. But in general, I have explained you what is a field and what is a Galois field and how to define it. But since I'm interested only in the binary field at present, so I will talk about the binary field. So when I say 4 tuples, it means that 4 bits will be there. Total number of combinations will be 16, and that's how 16 possible combinations will form the vector space, and that vector space is represented by V4. What will be a subset? An example of a subset V4 that forms a subspaces. So so out of these 16 combinations, I take 4 combinations. So this will be called as a subset. Now let me come back to the slides where I will explain that what will be a subset. What should a subset satisfy? What properties should a subset satisfy? All right. So examples of vector spaces, the set of binary n tuples denoted by Vn. So in general, it can be n tuples, and that subspace will be defined as Vn. for as an example, I'm taking the case of V4. That means 16 combinations will be there. Now, what will be a vector subspace? A subset S of the vector space Vn is called a subspace if. Now, this is very important actually. The all zero vector should be in the subspace. Now, I can call a space as a subspace of the vector space, right? This is vector space containing all the possible combinations, but I will define a subspace. What should be the characteristics of the subspace? It should include the all zero vector, that is number one. The sum of any two vectors in S, that is subspace, is also in S. For example, this is a case of subspace. This is the four elements will form a subspace. Zero vector, all zero vector is there, and if you add this any of the two vectors, then the resultant vector should also be present in the subspace. Then that subspace will be called as a vector subspace of this V4. That means a subset S of vector space is called a subspace if the addition of two elements results in an element in the subspace and all zero vectors should be there. And this property, the sum of any two, this property, which is the sum of any two vectors in S, is also in S. This property is called the closure property, right? The subspace should follow the closure property and the all zero vector. Now, what is a spanning set? I will come back to spanning set and basis. Let me explain the things once. Let me introduce the concept of linear block codes. Then I will come back to explaining what is spanning set and what is basis. Right? What is a linear block code? Linear block code is set C, which is a subset of Vn with cardinality 2 to the power k, is called a linear block code if and only if it is a subspace of the vector space Vn. So Vk leads to C and it is a subspace of Vn, right? So this is the actual definition of the linear block code, but let me explain with an example what is this is the diagram that will help you to understand the concept of linear block code. For example, I consider k bits, k information bits, k message bits. Now the message bits can be, I can consider one bit as a message bit, as a message. I can have two bits as message, three bits as message. So in general, let me say that there are k bits in the message, in the data block. So my message bits are k, right? And I do the channel encoding. I do the channel encoding means I introduce some more parity bits into these k bits. Those parity bits are I will include to excuse me. I will include those parity bits to detect and correct the errors. So that means I am actually adding redundancy into my message bits. So what will be the resultant number of bits? Let's say these bits are n. N will be always greater than k. So k are the greater than equal to k. So k are the message bits. I am doing channel coding with little more number of bits, which we call as the parity bits, and I will get as a result n bits. So n is always greater than k. So n minus k are the redundant bits that I will introduce using the channel coding. And what is the rate of this encoder? It is k by n. K are the input bits and n are the output bits. So RC, which is k by n, this is known as code rate, right? This is known as code rate. So and a linear block code can be expressed as n comma k. N comma k means n is the number of bits in the code word. So this will be called as a code word and this will be called as a data block. N comma k. And any linear block code will be represented as n comma k. N represents the number of bits in the code word, and k is the number of information bits or message bits. All right. Now, okay, let me see whether I can. Okay, I will have to. one point I need to explain is that I am covering this topic from Bernard's Clark book. I will send it to you. The book, it's a, I think 60 MB book. So, but I will send it through the drive, through the Google Drive. So now let me explain this concept. So n tuples are there. That means n tuples means how many bits I am considered. N is for the number of bits in the code word. N tuple means number of bits in the code word, right? So total number of combinations, how many total number of combinations will be there? As I took the example here, in which I considered 4 tuples, that means 16 total possible combinations. This is known as vector space. Now this diagram, all the dots are actually representing the number of combination, number of elements in the vector space. All the dots, all these dots, this is just the diagrammatic representation of the concept, right? So all the dots actually represents the number of elements in the vector space. For example, this for V4, how many dots will be there? There will be 16 dots. All right, so that means every so there will be 16 dots, meaning by there will, every code word will be 4 tuples. Every code word will be 4 tuples. Now what is k? K, as is explained through this diagram, k are the number of message bits. So how many combinations are possible? 2 raised to the power k. How many bits are there in the code word? 2 raised to the power, how many bits are there? N bits. How many combinations are possible? 2 raised to the power n. So 2 factors are there. One is 2 raised to the power k, the other is 2 raised to the power n. All right. How many message bits are there? How many message bits are there? K bits are there. K are the message bits. So how many possible combinations of messages are there? 2 raised to the power k. How many possible combinations of code word are there? 2 raised to the power n. Obviously, when n is greater than k, 2 raised to the power n will be more as compared to 2 raised to the power k. But we will select some of the code words, right? All the message blocks will be, all the message blocks will be mapped to one of the code word, right? For example, if I take the k, so this is my, these are my code words. So let's say my message bits are I consider k equal to 2. How many possible combinations will be there? 4 combinations will be there. 0 0 0 1 1 0 and 1 1. But how many possible combinations of the code word are there? 16 possible combinations. I need only 4 code words from this set to map all the combinations of the input data block to the code word. But what code word what code words out of these 16 possible combinations should I select? So I need 4 code words to be mapped to 4 message combinations. If I take k equal to 2, so that means the subspace, this subspace will consist of 4 in a sense that I will select 4 combinations out of these 16 combinations so that I can map the 2 bits at the input to the code words. Because 4 possible combinations are there at the input, 16 possible combinations are there at the output, but I select 4 out of the possible code word combination. Now, what 4 code words should I select? And that will be called as a subspace. So this property will have this exponential. I should select an all 0 vector out of the possible 16 combinations. First element will be all zeros vector. That is a must. The second is that I should select those code words. The addition of those code words should result into the sum of any 2 code words should also be there in the subspace. So that requirement, if I do, I can select these. I can select out of 16 combinations. I can select these 4 code words, which I can map if I give to the input 0 0, I can say that is mapped, output will be 0 0 0 0. If I give 0 1, output will be 0 1 0 1. If I give 1 0, output will be 1 0 1 0. If I give 1 1, the output will be 1 1 1 1. Right? So there is a one-to-one mapping between the input and the output and the code word. Right? Let me explain it with this diagram. Okay, so VK are the number of combinations at the input. Vn are the number of possible combinations at the output, right? And I have to select, because how many combinations are required at the input? 4 or VK. So I must select VK out of this Vn. As an example, if I take the case of, let's say this is my linear block code n comma k. If I select n as 4 and k as 2, how many possible combinations of the bits are there at the input? 4 combinations. And my code, my n is equal to 4. So how many possible combinations are there? 16. 4 combinations at the input, 16 combinations at the output. So from the output combination, I have to select only 4, right? But which 4 I need to select so that it becomes a subspace? I must include the all zeros vector. I must include the those code words, the sum of which should also be there in the subspace. That's the condition. That condition is known as the closure property, right? So 2 raised to the power k will be less than 2 raised to the power n. So that's what is explained in this diagram. Just a diagrammatic explanation that all these dots represent 2 raised to the power n. These selected dots are representing 2 raised to the power k. So 2 raised to the power k n tuples. 2 raised to the power k n tuples mean, if I take the example of k equal to 2 and n equal to 4, it will be 4 possible code words of 4 tuples each. 4 tuples each means 4 bits in the output in the code word constitute the subspace of the code words, and this is the entire space. So all dots represent the entire space, and whatever is selected will be called as the subspace. So this will be equal to 2 raised to the power k, and this will be equal to 2 raised to the power n. So we can form, what we can do, how we can do this mapping. I can put a lookup table in which I will, on one side I will put the number of combinations of the input, on the other side I will put the number of combinations of the output. So there will be a one-to-one mapping. But the problem is that if the number of bits, number of k bits are large and number of n bits are also large. For example, if I consider 170, n as 170 and k as 7, this n I consider as 200 and k I consider as, let's say, 50 bits for the message block and 200 bits for the output block or the code words. Every code word will have 200 bits. Every message block will have 50 bits. So how many possible combinations of code words are there? 2 raised to the power 200. And how many possible combinations of the message blocks are there? 2 raised to the power 50. It's a huge number. So lookup table approach will not be will not make sense. So what we will do, how many possible combinations? No, I will not specifically take an example. Rather, I will talk in terms of k and n only. So 2 raised to the power k message combinations and 2 raised to the power n code word combinations, right? I require how many code words from the code book? I require 2 raised to the power k code words from the code book, right? Now, there is a concept here. I will come to the Hamming distance and all afterwards. Yeah. What I can do is that, so I need 2 raised to the power k or vk. 2 raised to the power k will be equal to vk, and 2 raised to the power n will be equal to vn, right? So this mapping has to be done. Rather than considering the lookup table approach, right? where the input combination of bits will be mapped directly to the output combination. What I will consider is, I will consider only k vectors, only k vectors from the vector space, right? From this Vn, I will consider only k vectors. It's not 2 raised to the power k, but only k. That means if my linear block code is with the specification 4, 2, what is the value of n? N is 4. And what is the value of k? It is 2. So how many vectors I need to consider? Only 2 vectors. And what I will do with those 2 vectors? A matrix G is constructed by taking as its rows the vectors of, so I will take only 2 vectors, and I will put those 2 vectors in a matrix. That matrix is called as the generating matrix, and using those k vectors only, I will be able to find out 2 raised to the power k code words. Right? I will explain the method like this. Okay, so this is the method. Encoding in n comma k block code. So how do you do the encoding? Here m represents a message vector having elements as m1, m2, mk. If k is equal to 2, that means it will be m1 comma m2. 2 bits will be there. If k is 3, so it will be m1, m2, m3. 3 bits will be there, right? And G is the generating matrix. How many vectors will be there in the generating matrix? Only k vectors will be there. Only k code words will be there. V1, V2, Vk, right? And how will I generate the code words? I will generate the respective code words by multiplying the message, because I have to find out, let's say I have to find out the code word corresponding to the message combinations, right? For example, 00 should map to which code word? How will I find out? I will have this generating matrix. This message will be multiplied with the generating. This is the matrix multiplication. So message will be multiplied with the generating matrix. If it is, let's say 00, so my 00 will be multiplied by the generating matrix here, and I will get the code word. So in general, for any n comma k linear block code, how to generate the code word? It is by multiplying the message bits with the generating matrix. The rows of G, the important thing about the generating matrix is that the rows of G, this V1, V2, Vk, these are actually the rows. This will contain elements, right? So V1, how many elements will be there? Vk, these are the Vk elements, right? These rows of G should be independent, right? So that's what, this is the formation of the generating matrix. Now, how many rows will be there in the generating matrix? There will be k rows. How many elements will be there in the generating matrix? In one row, there will be n elements in the n elements in the n elements in each row, right? Now, code vectors by convention are usually designated as row vectors. So every row vector will be a code vector. Thus, the message M, a sequence of k message bits, is shown below as a row vector. So message is basically a row vector, right? The generation of the code word U is written in matrix notation as U equal to M into G. Now, this Cij, this is the matrix multiplication. You all know how to do the matrix multiplication. This is just the mathematical formulation of the multiplication done. Let us take an example here. An example is, let's say this is my G generating matrix, and I can clearly see that 3 rows are there. If 3 rows are there, that means how many input bits? How many input bits are making one input block? Because there, how many rows will be there? There will be k rows only. V1, V2, V3. If you see this here, there will be only k rows, V1, V2, and Vk. So from this generating matrix, I can clearly see what is the specification of the linear block code? So how many elements are there in this row? 1, 2, 3, 4, 5, and 6. So 6 elements are there in each row. Every row is representing a will lead to a code word, right? So number of elements in the row of this generating matrix will be equal to n. That means in this linear block code, n equal to 6. And how many rows are there? 1, 2, 3. This is 3. So this, what is the specifications of the linear block code that will be generated by this generating matrix? It will be 6, 3. 6, n equal to 6 and k equal to 3, right? So v1, v2, v3 are 3 linearly independent vectors, a subset of the 8 code word. So this is actually a subset of the 8 code words. Why 8 code word? Because 3 bits will have to lead to, we require 8 code words actually. There are how many total possible combinations of the vector spaces? 2 raised to the power 6. 2 raised to the power 6 is 2 to the 4. What is 2 to the power? It is 64. No, 16, 32, and 64. So 64 combinations are there. In the 64 total code words are there. What is the what is the message block size? It is 3. So 2 raised to the power 3 is 8. Total number of possible combinations of the code word are 64. How many we require? We require only 8 because we have the input combinations as 2 to the power 3. So 2 to the power 3 message combinations will, so we require only 8 code words for a linear mapping. But how many total are there? 64, right? So we select the generating matrix. This is the generating matrix of this specification. This generating matrix will be used to generate the code words, right? So this is my, let's say if my message bits are 110, and this is my generating matrix. So I will use this matrix as multiplication with 110. So if you do this multiplication, you will see that what is the code word that will be resulting? 101110 by this multiplication. This is my M, this is my G. I will take G from here, multiplication done, and that will be my code. All right. Now, this is the example here. This is the message vector. This is the code word. Message vector, this is 6, 3. Message vector is consisting of 3 bits, whereas the code word is consisting of 6 bits. Total possible combinations of 6 bits are 2 to the power 6, but I require only 8 combinations. What code word combination I should have? All zeros vector has to be there, and the addition of any of the vector, the result should also be there in this subspace. Then only this will be called as a code book. And how can I generate the code words from these message vectors? I can generate using this generating matrix. So what I need to generate these code words, I need the generating matrix, and I need any what possible combination of bits I need to find out the code word for. Now, this is the example of linear block code. Now there are systematic block codes. What are systematic block codes? The specifications remain the same, in which n comma k, for a systematic code, the first or maybe the last, I will whatever we will consider, I will consider the last part. The k elements in the code word are information bits. So what are systematic block code? In the systematic codes, the information bits, the message bits will be part of the code word. The message bits, for example, these are my message bits 000, 100. These will be part of the code word. Now, if you can see here, this 000 are the 3 bits in the last. 100 are the 3 bits in the last. This 010 are the 3 bits in the last 3 bits of the code word. So message bits are a part of the code word, right? And what are the first 3 bits? This 000, this 110, this 011. These are the parity bits in the code word. All right. So for a systematic code, the the first k or the last, I will talk about last only. Last k elements in the code word are actually information bits. So what should a generating matrix should look like in that case? It should consist of P, which is a matrix only, and IK. IK is another matrix. IK is an identity matrix. What are the dimensions of the identity matrix? K cross K. PK are the parity matrix. What are the dimensions of PK? K cross n minus K. And I will generate what will be the size of the code word? Of course, I have to take n, U1, U2, UN. This is the code word, general representation of the code word, right? P1, P2, Pn minus K. These are the parity bits. How many parity bits will be there? N minus K. M1, M2, and Mk. These will be the message bits. And what should the generating matrix should look like? It should be parity bits and the identity matrix. So as an example, I can describe it like this: U1, U2, UN. These are the message. These are the code word elements. M1, M2 up to Mk. These are the message bits. P11, P12 up to P1, comma n minus K. These are the parity bits. And this 1, 0, 0. All the diagonal elements are 1. When you will multiply this generating matrix with this message vector, what you will find out is that message bits will take the last portion of the code word automatically, because this is the identity matrix. So where UI, every element, every code word will be by the, it's just the mathematical, it's just the multiplication explained here. Now, given the message k tuple, so how many bits are what is the size of the message? It is k tuple, m equal to, this is a vector, this bold m is a vector, m1, m2, mk, these are the elements of the vector. And the general code vector and is an n tuple vector. So this capital U, this bold U is actually the code vector, and U1, U2 up to, these are the elements in the code word. The elements mean the number of bits in the code word. And the systematic code vector will be U. The first n minus k will be the parity bits. The last k bits will be the message bits. All right. And this P1, what is P1? P1 is the, let me explain here. P1 is M1, P1. So P1, what I will get, this is the, in the code word, first n minus k bits will be the parity bits, and the last k bits will be the message bits. For example, I take the case of n equal to 6 and k equal to 3. Every code word, 3 will be 6 minus 3 will be the parity bits. That means 3 parity bits are there and 3 message bits are there. So this parity, how to generate this parity bit P1? P1 will be generated by M1 P11, M2 M1 P. You can see from here M1 P11, M2 P21. How this first parity bit will be generated? M1 multiplied with P11, M2 multiplied with P21. This is the generating matrix. This will be given to you to solve any question. Message bits will be given to you, generating matrix will be given to you. How to generate the parity bit? This P1 will be equal to M1 P11, M2 P21, and MK PK1, as is given here. And similarly for P2 and similarly for Pn minus k, because n minus k parity bits are there. So systematic code words are sometimes written so that the message bits occupy the left. So I'm not, let's not go into the left hand portion of the code word. How you can achieve that? That can be achieved if you put this identity matrix on. You just interchange the parity matrix, parity portion of the generating matrix, and the identity matrix portion of the generating matrix. Right? If these are exchanged, so you will get the message bits at the left. Now you can see that if this is the generating matrix, this is my code word U. The output of the multiplication of the message bits and the generating matrix will be my code word. So let's say this is my generating matrix. My first element of the code word will be U1. How to get what U1 will be equal to? U1 will be equal to M1 and plus M3, because M2 will be multiplied by 0. This is just to explain you how to generate the elements of the code word. All right. Now, the question is that, so how this is how we can let's say one combination of message bits come at the transmitter, will be fed as an input to the channel coder. Channel coder will give k bits will be fed to the channel coder, n bits will be transmitted, right? That will be a linear block code, n comma k, in this fashion. This is linear block encoding using this generating matrix. Okay, now we have to decode the bits also, whatever the code word that will, because we wanted to transmit 3 bits, but we are sending 6 bits into the channel. So at the receiver, 6 bits will be received, but we want to know what is the combination of the 3 bits that was sent actually. So how to do that? Now for a linear code, we can find a matrix H. What are the dimensions of the H matrix? N minus k cross n, such that its rows are orthogonal to the rows of G. What is G? G is the generating matrix. Now corresponding to every G, there will be a matrix H. What are the dimensions of matrix G? Dimensions of matrix G are k cross n minus k cross n. Right? How many rows are there? K. How many columns are there? N. What are the dimensions of the H matrix? This is also called parity check matrix, right? H is called parity check matrix. G is called the generating matrix. Dimensions of G are k cross n. Dimensions of H are n minus k cross n. Now, we can always find a parity check matrix corresponding to every generating matrix. What should be the caveat here? What should be the condition? The condition should be G into H transpose should be equal to a 0 matrix. The multiplication of the G matrix with H matrix should be a 0 matrix. So H is called the parity check matrix and its rows are linearly independent. Again, for systematic linear block codes, H will be given as IN minus K P transpose. You must see what is how to write the generating matrix. P, this line is there just to indicate the separation between the parity part and the identity matrix, right? So this is how the G is written, but how the H is written? H is written as IN minus K P transpose. So if you are given with G, you can always write H. You can write an identity matrix with this specification n minus k cross, right? So this is P transpose. Let me, what is P transpose? P transpose, I can write it as IN minus k, and lower portion will be the parity check matrix. Now, as an example, I can do this. So earlier, what was my G? Let me show you. This is my G. Actually, this is the generating matrix in which the elements are arranged like this: P11, P12, P1, comma n minus k, and this is the identity matrix. How to write the parity check matrix? The parity from the generating matrix, I can write the parity check matrix as this. So the upper portion will be identity matrix. What should be the size of the identity matrix? N minus k cross n minus k, and n minus k, right? And what should be the size of the what should be n minus k cross n minus k will be the size of the identity matrix, and what should be the size of the parity check matrix? So I n minus k and then parity check matrix. So it will be P11. The size will be k cross n minus k, right? Just what we have done here is that this is the generating set. The parity portion is actually the identity matrix. Let me show you once again. So I have to write H as this. This is IN minus K and P transpose, right? The parity check portion of the generating matrix has to be written as the transpose. Once I will do the transpose, it will come at the lower portion like this. So this is my P transpose, P11, P12, because the, let me show you once again. The rows, the rows actually become the columns, and the columns become the row. All right. So this is my parity check. So the point is that from the generating set of vectors, I can generate the parity check matrix at any point of time. So it is easy to, now we can verify that the product, what is this product? This product is the code word into the parity check matrix of each code word generated by G and the H yields. Now the product of the code word, every code word, multiplication with the transpose of the parity check matrix will always lead to zero matrix, where the parity bits are thus once the parity check matrix is constructed to fulfill the foregoing orthogonality requirement. What is orthogonality requirement? It is G H transpose equal to zero matrix. All right. Now this is data source for this general block diagram of the communication system, in which the channel encoding is done, then modulation is done, the signal is transmitted, and at the receiver you demodulate the signal, and you receive a vector R, which is a noisy vector which may be having errors, right? So what R will be equal to? R will be equal to whatever the code word was transmitted from the transmitter side. Received is the R, received code word is R. Maybe some bits are in error, we don't know. So how can I represent R? R is actually equal to U, which was transmitted, plus the error vector, plus because if let's say plus the error vector means the whatever the bits that will be in error. Error means if one will be there at the receiver end, we will receive it as 0. If any bit was 0, we will receive at the receiver that bit as 1. So that bit will be in error. So U plus E, received vector, will be equal to the transmitted vector plus the error vector or the error pattern. So this is my received vector with elements R1, R2, Rn. This is the received code word. And if any bit will be in error, so that will be the correspondingly error pattern will be, let's say the first bit was in error, right? If the first bit will be in error, the error pattern will be 1 0 0 0 0. All others will be 0 only except the first bit. So that is the error vector. So my received vector will be equal to U, the code word which was transmitted, and this E is the error vector. There is a concept called it is 12:10. I will continue with this lecture tomorrow also, and tomorrow probably I will finish with the linear block code. If you see the assignment 2, you will find that there are all the questions are based on linear block. Most of the questions are based on linear block codes, and some questions are based on convolutional code that we will also do in the coming lecture. If any questions are there, please ask. Okay, I will continue with the with this concept of linear block codes. I will just review some portion which I did today. I will review it tomorrow also, and I will do the rest of the portion also in tomorrow's class. Thank you.